Hello, I'm Rebecca Barnes and welcome to the Science ESA vodcast. In this episode, we'll investigate our closest star, the Sun, find out why it's the central engine of the solar system, and look at Ulysses, SOHO and Cluster, the European space missions that have been key to advancing our understanding of the Sun. Life on Earth relies on the Sun for light and heat. The energy released by our nearest star has allowed humankind to survive for hundreds of thousands of years. Today, we seek to understand how the Sun works, why it changes, and how these changes influence us here on Earth. Some of the variations of the quality and quantity of light from the Sun over short and long timescales most certainly affect the Earth's environment, but how is uncertain. With the dawn of the space age, we learned that the Sun also affects the space environment around our home planet. The conditions on the Sun, the solar equivalent of wind and storms, can influence the performance and reliability of the technology and satellite services that our lives are becoming increasingly dependent on. Despite its critical role in our lives, the Sun is just an average star. More specifically, is a small yellow dwarf star located on the main sequence of the Hertzsprung-Russell diagram. It is by far the largest object in the solar system. With a diameter that is over 100 times that of the Earth, the Sun contains 99.8% of the mass of the entire solar system.
The most dominant elements in the Sun are hydrogen and helium, with a tiny fraction of other heavier elements such as carbon, nitrogen, and oxygen. Due to its high temperature, the Sun's matter is in the state of an ionized gas, the so-called plasma. Protons and electrons, stripped from atoms, move freely throughout the solar interior. Almost half the mass of the Sun is densely packed within its core. It is here that the Sun's energy is generated. The temperature in the core of the Sun reaches over 15 million Kelvin. Nuclei can be packed together more tightly than atoms. The Sun's outer layers squeeze the nuclei in the core, increasing the pressure and the temperature. The resulting pressure is immense and provides the right conditions for nuclear fusion to take place. The fast-moving protons in the Sun's core occasionally collide and fuse, forming deuterium. This triggers a three-step chain of events that fuse 4 protons into an alpha particle, a helium nucleus made up of 2 protons and 2 neutrons. This helium nucleus is slightly lighter than the 4 protons that combine to make it. This difference in mass is converted into energy according to Einstein's famous equation E equals mc squared. Releasing energy equivalent to exploding approximately 92 billion megatons of the explosive TNT every second. Neutrinos are also produced in large quantities as a byproduct of the chain reaction. The energy released during nuclear fusion is in the form of gamma rays. These highly energetic photons travel outwards from the core and reach the radiative zone. Here, in the still very dense plasma, the photons are absorbed, re-emitted, and deflected so much that it can take an individual photon hundreds of thousands of years to pass through this zone. The convection zone extends from the radiative zone to the surface of the Sun. In this zone, the temperature drops to 2 million Kelvin, which is too cool to allow energy transport by radiation. Instead, the energy creates huge convection cells of plasma which bubble to the surface. The light that we see is emitted from the photosphere. This is also the region from where most of the Sun's energy escapes into space. The temperature here is just below 6,000 Kelvin. The photosphere is not smooth or uniform in appearance. Brighter areas are caused by hot material welling up from below, and the darker areas by cooler material sinking. In the chromosphere, the temperature rises to 10 to 20,000 Kelvin. It is the interface to the outermost layer of the solar atmosphere, the corona, which consists of highly rarefied gas with temperatures of several million Kelvin. The plasma in this region emits most of its energy at ultraviolet and X-ray wavelengths. The solar corona conducts heat so well that the sun's gravity cannot hold on to all of the hot plasma. As a result, a supersonic stream of charged particles, mostly electrons and protons, flows from the sun in all directions. This is the solar wind.
The sun is extremely dynamic, constantly churning and quivering. This activity continually throws up unexpected features and behavior. Much of the observed solar activity appears to be directly connected to the properties of its complex and changing magnetic field.
The sun's magnetic field in its simplest form is like a huge bar magnet. In part, this field is due to the moving convection cells that contain electrically charged particles, positive ions, and electrons. These magnetic field lines can at times break through the visible surface of the photosphere and form sunspots. The intense magnetic fields inhibit the flow of energy from the convection zone below, leaving the sunspot cooler and therefore darker than the surrounding photosphere. Sometimes, without warning, the relatively calm solar atmosphere above active regions can be torn apart by catastrophic solar flares, releasing a huge amount of energy. When viewed in X-rays, a solar flare can be 100,000 times brighter than the entire sun. Another dramatic phenomenon, also energized by the magnetic fields of the sun, ejects billions of tons of material in the form of electrons and protons into space at high speeds. This is known as a coronal mass ejection. These storms from the sun expand rapidly and within a few days can grow to over 100 million kilometers in size.
During a coronal mass ejection event, billions of tons of gas pour out of the sun. We are living in the extended atmosphere of a star and are therefore exposed to the variations and activity of the sun. If propagating in the right direction, these particles can blast across the 150 million kilometers between the sun and the Earth in just a few days. In addition, the solar wind dominates the space between the planets of the solar system.
Fortunately for life on Earth, our own planet's magnetic field protects us, preventing the charged particles from hitting the surface. There is a recognizable boundary layer where the solar wind and the Earth's magnetic field meet. When the energetic particles of the solar wind impact the Earth's magnetic shield, they are suddenly slowed down, causing a shock on the sun-facing side. Beneath this boundary is the magnetosphere, which is molded as the flow of the particles is diverted around the Earth. The magnetosphere's long tail stretches millions of kilometers away from the sun. There are two weak points in the Earth's magnetic defense to the solar wind. These occur near to the Earth's north and south magnetic poles. When solar wind particles leak into the magnetosphere, they spiral towards Earth along the magnetic field lines. On reaching the upper atmosphere, these particles interact with the gases present, causing them to emit photons and glow. This phenomenon is known as the aurora. Many years of observing the sun have revealed that solar activity appears to vary in a regular manner from a maximum to a minimum over an 11-year cycle. This solar cycle coincides with changes to the polarity of the Sun's magnetic field, which reverses around the time of a solar maximum.
The importance of understanding the Sun-Earth connection has led to a fleet of solar sentinels monitoring our star. These missions provide a wealth of data which have transformed the way scientists view the Sun and its effect on the surrounding space. This information is crucial for a better understanding of the long-term behavior of the Sun and its impact on the Earth and its environment. Let's have a look at 3 of these missions, each of which provides a unique perspective of the Sun. The ESA-NASA Solar and Heliospheric Observatory, or SOHO, stares at the Sun from a distance of 1.5 million kilometers away from the Earth, at the first Lagrange point. Here, the combined gravity of the Earth and the Sun keeps the spacecraft in an orbit locked to the Earth-Sun line. From this position, SOHO has an uninterrupted view of the Sun and can therefore make observations 24 hours a day. SOHO was designed to study the internal structure of the Sun, its extended outer atmosphere, the corona, and the origin of the solar wind. Launched in 1995, SOHO has watched the Sun over a complete solar cycle, supplying scientists with valuable data to help understand the highs and lows of the Sun's long-term behavior.
To probe the solar interior, scientists monitor the Sun's surface as it heaves rhythmically with a period of about 5 minutes. These motions are due to sound waves reverberating through the solar interior, sensing the layers and movement of underlying hot gas. Analyzing these sound waves using a technique known as helioseismology, scientists have revealed the first images of the Sun's convection zone and the structure of sunspots below the surface. Using this technique, which is similar to the method used to study earthquakes, scientists were also able to detect developing sunspots on the far side of the Sun. Sunspots are regions of strong magnetic fields that speed up the sound waves. These sound waves rebound internally from the solar surface and hence are detected on the near side of the Sun. To image the solar corona, one instrument on board SOHO uses a coronagraph to make an artificial eclipse to mask the dazzlingly bright disk of the Sun. Why the gas in the Sun's corona is so hot is one of the mysteries that SOHO is helping to solve. Using data from SOHO, scientists have analyzed the appearances and disappearances of tens of thousands of small magnetic concentrations on the solar surface. This magnetic carpet is highly dynamic and rapidly changing. Energy flows from the magnetic loops when they interact, producing electrical and magnetic short circuits. The laws of electromagnetism do not allow two magnetic field lines to intersect. But when field lines collide, they snap and subsequently reconnect. This mechanism is known as magnetic reconnection. The very strong electric currents induced during the reconnection process heat the corona to a temperature of several million degrees. The solar wind consists of 2 components: the fast solar wind, which is close in composition to the Sun's photosphere, and the slow solar wind, that is more like the solar corona's composition. SOHO has measured for the first time the acceleration profile of both components of the solar wind and has found that the acceleration takes place surprisingly close to the solar surface. It also observed the fast solar wind flowing from funnel-shaped magnetic fields that pass through coronal holes, areas of the solar corona that are cooler and lower in density.
Ulysses was launched in 1990 on a 5-year mission to become the first spacecraft to study the unknown environment of space above and below the poles of the Sun. In order to get into its unique orbit around the solar poles, Ulysses had to perform a slingshot maneuver around Jupiter. When the mission ended in 2009, it had orbited the solar poles 3 times, providing a view of the Sun never seen before. This incredible mission did not just study the Sun, it also studied the interaction of the material emitted by the Sun with inflowing interstellar material. The Ulysses mission achieved numerous firsts and discoveries. Let's have a look at a few of them.
The extended length of the Ulysses mission allowed the Sun to be monitored during periods of minimum and maximum solar activity. It was data from this mission that showed that the polarity reversal of the Sun's magnetic field carried into the heliosphere by the solar wind was a surprisingly simple process. It simply appears to rotate through 180 degrees from sunspot minimum through sunspot maximum and back to sunspot minimum again. Ulysses explored the solar wind from all angles, producing the first 3-dimensional view of it in the heliosphere and monitored how it changed with time. Prior to Ulysses, solar wind measurements were only available from satellites located close to the Sun's equatorial plane. These measurements were assumed to represent the dominant state of the wind. Ulysses showed that a faster solar wind flow, originating at high latitudes, dominates the heliosphere for most of the solar activity cycle. Astronomical observations suggest that the Sun is currently moving through a warm cloud of interstellar dust and gas. Ulysses was able to make the first direct measurements of the dust and helium from this local cloud that has penetrated deep into the heliosphere. Before Ulysses was launched, it was thought that charged energetic particles created during solar storms would be confined to latitudes close to the location of the storms. Charged particles are constrained to move along magnetic field lines, and the heliospheric magnetic field was not expected to have large excursions in latitude. However, Ulysses observed large numbers of energetic particles over the solar poles, far away from the location of the solar storms that created them. This discovery has forced scientists to revisit their ideas about the magnetic field and how particles are transported in the heliosphere.
In 2000, ESA launched Cluster, the first space mission able to study the Earth's space environment in 3 dimensions. It consists of a constellation of 4 identical spacecraft flying information around the Earth. Each satellite is equipped with the same set of scientific instruments that simultaneously measure particles and waves in near-Earth space. The resulting picture, as produced by these 4 spacecraft, can only be achieved using multi-point measurements. Cluster, for the first time, unravels how this environment varies in space and with time. Cluster data have already led to a wealth of new results, and this exciting yield is set to continue.
Just as SOHO observes the Sun and Ulysses the evolution of solar emissions through the interplanetary medium, Cluster captures how the solar wind affects the Earth's magnetosphere. Data from Cluster taken during extreme solar events have shown that the charged particles arrive at the Earth's magnetosphere with a higher speed and greater density than when transported by a regular solar wind. This causes the magnetosphere to be extremely compressed and the Earth's magnetic field lines to oscillate and accelerate particles in the Van Allen radiation belts. Cluster's observations of these phenomena allow us to refine models of our near-Earth environment where commercial and navigation satellites orbit to better predict effects of solar storms on Earth. Another important phenomenon in which data from the Cluster mission have enabled a huge leap forward in understanding, is magnetic reconnection. Reconnection is the key mechanism by which the solar wind can penetrate the Earth's magnetic shield, propelling the high-energy solar wind particles towards the Earth. The 4 Cluster spacecraft enabled in particular the first three-dimensional observation of the heart of the reconnection process. This process occurs across the universe at distances too vast for it to be studied in detail. However, Cluster can study this important phenomenon close up. In 2005, Cluster solved a long-standing problem: why the magnetosphere was found to be constantly topped up with plasma from the solar wind, even though it should have been acting as a barrier to this material. Cluster discovered ejected solar material trapped in large vortex structures, hundreds of thousands of kilometers in size, high above the Earth. These vortices are caused by the fast-moving solar wind sliding past the slower-moving magnetosphere, similar to the process by which waves are whipped up by the wind sliding across the surface of the ocean. It is these vortices that are thought to provide a mechanism for plasma to tunnel its way into the magnetosphere. The high temperature of the solar corona enables matter to escape the sun's gravity as the solar wind. However, it is unclear how the solar wind is heated. Cluster data are helping to piece together the answer to this problem. It has been used to trace how the flow of energy in the solar wind is transferred from very large scales at its source, the corona, to small scales where it is dispersed. This is extremely challenging, and it's a bit like trying to understand how energy is transferred from the calm, smooth flow of a river down to the small, turbulent eddies and foam formed at the bottom of a waterfall. Cluster results showed the importance of electron physics in this process.
The space age made us realize just how fragile our planet is and the intricacy of its relationship with its local star. The complexity of the Sun from its interior to its atmosphere is perplexing. Many or most of the Sun's key physical processes operate on such large scales and over such long time periods that future generations of observations are required to resolve them. Cluster, SOHO and Ulysses allow the investigation of energy flow from the Sun to the Earth and the study of plasma processes in the Earth's magnetosphere driven by the solar wind input. The effect of having a fleet of spacecraft observing our Sun has given us extraordinary insight into the behavior of a rather ordinary but exceptionally important star, our Sun. I'm Rebecca Barnes. Thank you for watching the Science ESA vodcast.